Yeah, she's coughing a bit, and so yeah, that's why I kind of decided to stay home. Oh, hang on. I mean, I feel okay, but yeah, she's coughing quite a bit. So I was also, just staying home and taking care of her today too. But in the event that it is COVID, then I think it's better that I work from home for the time being. Thanks, I appreciate that. All right, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. First of all, I want to thank everyone. Thank you guys for being flexible. I know it was kind of a last-minute change, but yeah, my fiance has been coughing a lot over the weekend. We don't know if it's COVID or not, and so I think just out of out of an abundance of safety, I thought I have the flexibility to go virtual, and I'd rather do that and rather than put everyone at risk. So thank you everyone for being flexible and making kind of the last minute change to virtual. Once we get the results back, either way, then I'll you guys will be one of the first people I update, and then we can go from there. But for the time being, probably for the rest of this week, we're going to be virtual. Until we kind of know what her condition is. Yeah. All right. And so with that, thank you again, everybody. How's everybody doing? How's everyone? We're week 8, right? So how's everyone week 8? How's everyone's semester going so far? It's good. It's good. Midterms are over. It's good. It's always a good thing. Yep. Work. Yep. It's the calm before the next storm. So the next storm, the next set of midterms is always right around the corner. But at least it's good to get the first one done and over with. Yeah. Okay. And so the plan for today is we're going to continue our lecture notes on upper extremity biomechanics. Okay. And so we did 2 examples last time, both of them with the elbow. And so today I wanted to do 2 examples with the shoulder, just to kind of show you all how that's done. Okay, and so we'll do that. Okay, and then I don't think that'll probably take maybe about 30-ish minutes, and then we'll talk about some common injuries of the upper extremity, and then we'll start to move on to the lower extremity. Okay, so today's going to be a little bit of all over the place. So we'll be jumping around quite a bit, just because we're kind of caught in the middle of 2 lectures. Okay. One announcement I want to make before we get started is that I posted your homework 4 last Friday. Okay, and so that's available for you, and that's going to be due on October 20th, and so that's next Wednesday. Okay, so I wanted to make sure, because a lot of the homework has to do with performing the static biomechanical analysis, and so I wanted to make sure that I think we'll probably finish it up today, and you have a little bit over a week to complete it. Yeah. Is it as lengthy as the 401 homework? It is fairly lengthy, and so it's definitely not a light homework assignment. So I would definitely start it early, and then just because at least for me, but when I was prepping these notes and making these homework assignments, I'm a little bit rusty in free body diagrams, just because I don't really use it in my everyday research. And so if you guys kind of feel the same way, that you're a little bit rusty, then I would definitely start sooner. And once you run into stumbling blocks, you can feel free to reach out to me, and we can work it out together. Okay. And in this homework assignment, there's another, like a mini research question. And so, definitely keep an eye out for that one too. And so the theme for this homework assignment is going to be joints and upper extremities. And so I gave you 2 research questions centered around those things. And so I think the first question I gave you is, our first option is, you can either do a study on shoulder braces, okay, and basically study how effective those things are from the literature, okay. And then the other research question is about Tommy John surgery. And so if you're not familiar with that, that's a common, not common, but but I would say baseball players are probably the audience that gets them the most, and that has to do with with a tear in a ligament in your inner elbow. Okay. Okay. And remember, you only have to pick one, so you don't have to do both the research questions. Just do one or the other one. Okay. All right. Any questions I can answer before we get started today? Okay. All right. So let's go ahead and get started. Okay. All right. And so where we left off last week was we were doing static biomechanical analysis. Okay. Okay. And the idea with this type of analysis is that we're going to be doing free body diagrams of basically of different parts of the human body. Okay. Okay. Remember, the goal of a free body diagram is that we're going to basically sum up all the forces and all the moments, okay?
Professor?
Yep, what's up?
Oh, there's some noise coming.
Oh, is it like it's like a tapping sound from my?
No, there's like a ringing noise.
Oh, ringing noise. Okay, let me see.
Sounds like a vacuum.
Oh, is it constant?
It's
Oh, it
now
just
off.
stopped. It just
Oh,
stopped.
okay. 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 Yeah, keep me updated. See, because I am on my laptop mic. Shoot, I should have tried to find my microphone mic. Let me see. Let me try to bring it a little bit closer to my face. Let's see. My cat is also making some noises in the background too, so that also might be part of it too. But yeah. Let me know if it's hard to hear, and then you know, we'll make adjustments. Yeah. Okay. Right, and so you know we're going to be summing up the forces and the moments, you know, in these free body diagrams, and the main goal for these, or the reason we're doing this, is so that we can solve for basically the internal forces within the human body. Okay, and in particular, there's two categories of forces that we're looking at, and so the first category of forces that we want to find out how much force the muscles are exerting. Okay. Right. And then number two, the second thing that we're looking for is we want to find out how many reaction forces are occurring at the joints. Okay. Okay. All right. And so because you know these two things are, you know, good indications for how much strain is being placed in the body, right? And so generally speaking, you know, even though our muscles are capable of exerting large forces and our joints are fairly stable most of the time, when they're sustained to or when they're subject to, you know, high forces and high stresses, this can cause a lot of, you know, long time wear and tear on the body. Okay. All right. And so let's go ahead and start with another example. Okay, and so let's do a static analysis, a simple static analysis of a shoulder joint. Okay. All right, and so this will be a shoulder that's basically outstretched at a 90-degree angle. All right, and so the diagram looks something like this. And so we're going to consider, let's say this is the upper arm bone, so this is going to be the humerus, okay? This right here will be the lower arm bone, okay? And so this will be the ulna or the radius, okay? Here is the hand. And let's say that this hand is supporting a weight. And so this is basically the same as someone kind of outstretching their arms and holding a weight at the end, okay? All right, and so from these, you know, we have three weights that we're going to consider. And so we have the weight of the upper arm. Okay. Oh, actually, I'm going to club it all together. And so just to make it simple, let's say that we have the weight of the upper arm and the lower arm. We'll consider them together. And then we'll put that force here at the elbow joint, okay? And so this will be the weight of the arm, okay? The object obviously has a vertical weight as well, and so that'll be a weight W, okay? And then supporting this is going to be the deltoid muscle. Okay. So here's my crude drawing of the deltoid muscle, okay? Okay, and so remember what we talked about last week, that the deltoid muscle is mostly responsible for shoulder abduction, right? And so moving the arm away from the body, and so that's why this deltoid muscle kind of acts here, okay? And so it'll act with some direction, let's say like that. So we'll call that FM, okay? All right, and the joint that we're interested in is going to be the shoulder joint right here, okay? Okay. And let's say that we have a reaction force in the x direction, so we'll call this Jx. A reaction force in the y direction, we'll call that Jy. Okay. And what we're interested in solving for is given the weight of the arm and given the weight of the object, we're going to solve for these three quantities. Okay. All right, and so, because we're only solving for one muscle force, we have three unknowns, and so the three equations that we have are going to be perfect for this. Okay. All right, so before we make a free body diagram of this, let me go ahead and give some of the lengths, and so we'll call this LA. Okay, and so that's the length or the distance between the shoulder and the elbow joint. Okay. And the distance from the shoulder to the hand, we'll call that LW, okay? And so we need those lengths for when we sum up the moments around the shoulder joint, okay? Any questions on this? How's the audio? Is it still, is it okay? Or question?
That's good. The audio is good, but Professor, is the force of the deltoid acting at an angle theta, or?
Yes. Oh, yes. Thank you.
Label it, but
yeah. No, I forgot to label it. You're right. Yeah. So there is an angle there, theta. Thank you. Okay. All right. And so let's go ahead and I know we have all the forces on here already, but let's go ahead and draw kind of a simpler free body diagram so that we can sum up the forces really easily. Okay. All right. And so let's approximate this entire structure as just a rod. Okay. Okay, and so in the middle of this rod, we have the weight of the arm. Okay, then we have the weight of the object, W, okay? And then we have the muscle force, just like that, okay, with an angle theta. And then we have joint force in the X direction, joint force in the Y direction, okay? And then we have the distances here. So this is L, A, L, W, okay? Just to make it a little bit cleaner for us. Okay, and so now let's go ahead and sum up these forces in each of the directions, okay? And so we have some of the forces in the X direction, okay? And so this would be Jx minus. The only other force in the X direction is going to be from the muscle force. And so that's going to be Fm cosine theta, okay? It's going to be equal to 0. Okay, so that's our first equation. Sum of all the forces in the y direction, we have Jy plus Fm sine theta minus Wa minus W is equal to 0. Okay. Right, and so for now, we can't really do anything with those equations because they have too many unknowns. And so remember, the equation that we usually start with is the sum of the moments around the joint. Okay, and so we're going to sum up the moments around the shoulder joint. Okay, and so here we have two moments that are going to want to rotate clockwise, right? And so those two moments are going to be the weight of the arm and the weight of the object. Okay. Right, and so if you make the moment arm here, you can see that these are going to try to rotate it going this way, which is clockwise. Okay. All right, so let's input those as negative moments. Okay.
Professor?
Yeah.
What about the distance between the muscle force and the joint? Like, it's not perfectly, are we assuming that it's perfectly on top of each other?
Oh, you're right. Sorry. It's there is a distance there too. So this is going to be Lm. Yeah. Yeah, there has to be a distance because it has to give an opposing moment to the other stuff. Yeah, I just missed it. Yeah. All right, so we have minus WALA minus WLW. Okay, and then we have the the component of the muscle force that's going to contribute to rotation, which is just going to be the y component. And so we have Fm sine theta times Lm. Okay. And all this is equal to 0. Okay. All right. And so this last equation here only has one unknown. And so we can go ahead and solve this one straight up for that one unknown. Okay. And so if we solve for Fm, what we get is Fm is equal to WA LA plus W LW all divided by Lm sine of theta. Okay. Right, and so we'll just leave it as symbols for now. But you can go, but ideally you can plug in numbers for this and get a a numerical solution. Okay. All right, any questions on this so far? Okay. All right, and so I always really love variable solutions like this because this always gives us a chance to see how our answer depends on the different parameters or different variables in our problem. Okay, in particular for this one, I want to look at theta, okay? Where theta, remember, is the attachment angle. Okay, or the angle at which the muscle attaches to the bone. Okay, and so I'm interested in looking at how does our muscle force depend on this angle. Okay, and so you can see from this equation, first of all, it's in the denominator, right? And so that's kind of a noteworthy thing. And the trigonometric function that we're working with here is sine, right? And so what do we know about sine, right? And so as theta approaches 0, right? What does that do for sine theta, right? And so as theta approaches 0, sine theta also approaches 0, right? Okay. And so what this tells us is that, as the attachment angle gets closer and closer to 0, this means that the amount of force that the muscle has to exert just goes up and up and up, okay? Okay. And so this is relatively true in general, right? And so this doesn't just apply to the shoulder joint, but it applies to any muscle around any joint. Okay. And the primary reason for that is, as the attachment angle, shrinks, then the amount of force that's actually contributing to, providing a counter rotation shrinks more and more and more, right? Because if we break down that muscle force, right, and so if we say that, we kind of zoom in on that on the shoulder joint, okay, and so here is our muscle force, okay. We can break this up into two different components, right? And so we have one component that goes like this, okay, and we have another component that goes upwards like this, okay. Okay. And so the only component of this force that can actually provide a torque or rotation on the joint is going to be the perpendicular component right here, okay? And so, and as the attachment angle shrinks more and more and more, then this component here gets less and less and less, okay? Okay. Right, and so it's generally, you know, advantageous for the body just in terms of, you know, how much work the muscles have to do to have a higher attachment angle. Okay, and so for a joint like this, for the deltoid, a typical attachment angle is about 30 degrees. Okay. So that's actually not that shallow, and so it's actually not that bad. Okay. All right, and so you know, that's you know, that's kind of our first analysis of the shoulder. Okay. And so the last example that I want to do today is another example of the shoulder, but we're going to do it at a different angle. Okay. Because generally what happens is that the attachment angle doesn't always stay constant. Okay. So generally, the attachment angle will change depending on the position of the attached limbs. And so for this next example, we're going to analyze the same shoulder joint, but we're going to lower the shoulder down a little bit. Okay, and by lowering the arms down, that's also going to change the attachment angle by a certain amount. Okay. Okay. Any questions on this before we jump into that next example? Okay. All right. So let's go ahead and do that next example here. Okay. All right, so let's look at the same shoulder joint. Okay. And so all the lengths are the same as the last time, and same thing with the weight of the arm and the weight of the object. Okay. The difference here is that the elbow is going to be lowered to an angle theta A. Okay.
Professor, I have a question real quick.
Sure.
So like, I know we're doing simplified calculations for these, but
Yeah.
like, say for example, if we really wanted to do this in real life, how would you go about determining experimentally like where the total center of mass is for a person's arm? Because like it's going to be different, right, depending on the amount of muscle that they have concentrated in either area. Like if they
Oh,
have
for
a bigger
sure.
upper arm and a smaller forearm, the center of mass is going to be different. So like, how would we get an accurate measurement for that?
Oh, for sure. Yeah, no, it's definitely a good concern. And so for I think for kind of like in the older days, I think doctors will generally take a few key measurements, and so they'll take kind of like the diameter of your arm at you know, at certain key locations, and then they'll make some assumptions based on, you know, the general density of muscle and the density of bone in that area, and then they can use that to kind of place an approximate location for your center of mass. Nowadays, you know, technology is a little bit better, and so you can literally kind of stick your arm into a scanner, and then it'll kind of map out a topology of your entire arm. And then from there, you know, and then of course making some assumptions on the density of muscle mass, the density of bones, and the volume of your arm, then it can place a center of mass in those areas too. Yeah. And so a lot of it is very kind of technology dependent. And you're right too, that all these examples are really simple in the fact that we're only considering a single muscle firing. And so in reality, I think, you know, what they're going to be looking at more is, you know, they want to see how each of the muscles act kind of individually. And so, you know, there's all kinds of different metrics of, you know, if they're making this motion, then, you know, they expect these muscles to be firing, and all that stuff. And so, yeah, it's a lot of technology, but and honestly, a lot of the technology that I'm not sure how a lot of it works. I've kind of seen quite a lot of it myself, but kind of the inner workings of it, you know, I can kind of only speculate kind of based on kind of what I see. But that's kind of how I imagine those all those things working. Yeah. Mm-hmm. Mm-hmm. All right, and so by lowering the shoulder, this is going to change the attachment angle of the deltoid to a smaller angle, and for now we'll call that smaller angle theta 2. All right, and so the diagram looks something like this. And so you can see we've lowered the arm like that. Okay. Let's assume that we're still holding the same weight. Okay. And so this weight is going to be acting vertically like that. We have the weight of the arm. Okay. And then we have our deltoid muscle acting like this. Okay. And now this is making an angle theta 2 with respect to the arm. Okay. And then this new angle theta A that I just talked about, this is going to be this angle right here. Okay? And so previously this theta A was 90 degrees because we had our arm kind of horizontally outwards. Now it's kind of lower to something less than the 90 degrees. Okay. Just like last time, we have our distances. And so we have the muscle distance here, LM. We have the distance from the shoulder to the elbow joint, as we'll call that LA. Okay. And then we have the distance from the shoulder joint down to the weight as W, or LW, I'm sorry. Okay. And so just like we did on the last problem, we're going to compute the muscle force and the joint reaction forces. Or I guess in this case, you know, we're focusing just on the muscle force, but once you find the muscle force, you can plug it in and find the joint reaction forces. Okay. Okay. And in particular, what we're going to do is, after we compute the muscle force in this configuration, we're going to compare it to the muscle force from our previous example. Okay. All right. And so I'm just going to do one equation in this case, you know, because we're just interested in the muscle force. I'm just going to do the sum of the moments around the shoulder joint. Okay. All right. Any questions on this? Okay. All right. So we have to do a little bit of trigonometry here. Okay. And so because these we're all working at an angle here. Okay. Computing the distances, or I'm sorry, computing the moment arms for each of these forces is going to be a little bit tricky. Okay. All right. Not super tricky, but just requires a little bit more thought than before. Okay. All right. And so since these weight forces here are going vertically down, the moment arm, or the distance between those vertical forces and the joint, are going to be these horizontal distances here. Okay. And so the way that we're going to solve for these is we're going to use the length along the arm to those specific locations. Okay. And so we're going to use LA and LW. And then we're also going to utilize this angle right here too. Right? And so if you draw kind of the right triangle, okay, so let me just do the one for LA first. Okay. And so this is the triangle that I formed by making this this guy right here, okay? And so if the hypotenuse of this triangle was LA, and then that angle there shown is theta A, okay? And we want to get the horizontal distance here, okay? The way that we can compute this is just simply LA sine theta A, okay? All right, and so on the next page, when I write out the moments for each of the you know, and for each of the contributions here, you'll see me use this the sine term, and that's basically where it comes from. Okay. Okay, and so let's go ahead and run the moments for these, you know, for this joint. Okay. And so if we sum up the moments around the shoulder joint, once again we have two contributions that are producing a negative moment, because they want to rotate clockwise around the shoulder joint, okay? And so first one is going to be the weight of the arm. And so we have WA, LA, sine of theta A, okay? Remember this guy right here, this LA sine theta A, this is the moment arm for that force, okay? Right, and then the moment from the weight of the object is going to be W LW sine theta A. Okay. All right, and so those are the moments from the external loads. And so now let's go ahead and include the moment here from the muscle. Okay. And so for the muscle, this is going to have the same expression as before. And so this is going to be FM sine of theta 2 LM. Okay. And all this is equal to 0. Okay. All right. And so here we have an algebraic equation, and the only unknown here is going to be FM. And so let's go ahead and solve for it. Okay. And in fact, since this is the second configuration, I'm going to call this FM2. Okay. And so if we work out the algebra here, we get sine theta A divided by sine theta 2, okay, times W times LA plus WLW. Sorry, this is WALA. Okay, all divided by LM. All right, so this is the new muscle force that we get, you know, based on the new configuration. Okay. All right, and so once again, you'll see that we have this sine theta 2 in the denominator. Okay, and so once again, you know, just because we're in a different configuration here, we still see the same dependence on the attachment angle, right? And so just like the last example, so if the attachment angle goes down, then, you know, the amount of muscle force required is going to go up, okay? But in addition to that, we also have this extra term right here, okay, which is sine theta A, right? And so what this basically says is that, you know, depending on the orientation of the arm, then the amount of muscle force exerted is going to depend on that as well, okay? And this one has the opposite dependence because it's in the numerator, right? And so as theta A gets closer and closer to 90 degrees, which is, you know, which was our configuration last time, then this contribution is going to go up. But as the arm gets lower, then this contribution is going to go down, okay? All right, question. So would the sine theta A be a scalar? That's a good question. And so, you know, the answer to that question depends on if theta A itself is a scalar. And so, you know, I think there's an analysis you can do where you can kind of, you know, keep your arm fixed. And so if your arm is going to be fixed in a certain position, then sine theta A is going to be a scalar. But if you want to see how this force varies as you move the arm up and down, then you can have that as a variable and you can plot against it. Yeah. Mm-hmm. All right. And so that's the amount of force that we get for this example. Okay. Now let's compare this force to the result that we got from when the arm was at a 90-degree angle.
Professor?
Yep.
How come we don't have a angle component on the length for the muscle force?
Length for the muscle force. It's here. I just kind of pulled it out. I just pulled it out of the denominator. So that's our sine theta 2. Yeah. Yeah. So you'll see why I pulled it out of the denominator in a second here. But yeah, normally this is I think if you compare it to the last example, this is kind of right here. But I just pulled it out just so that we have this kind of ratio of sines on the outside. Yeah.
Oh, but I thought the theta 2 was the angle of attachment.
It is the angle of attachment. Yeah. Mm-hmm.
Oh wait, so how come we don't have like an angle on the length like we do for the?
Oh, I see what you mean. So how come there's no sine theta a on the denominator, right? And so it's because that this theta 2 right here, this theta 2 here is measured relative to the arm itself. And so the reason that doesn't change is because if the arm was horizontal like it was in the previous one, then we have this theta right here, okay? And it just so happened in this example that this theta is also measured relative to the horizontal because the arm is also horizontal. But when the arm is tilted, we still measure that angle with respect to the arm itself. Yeah. And so if that attachment angle was measured relative to some fixed horizontal, then we would have to factor in this theta a somehow. But generally, how attachment angles are defined is they're always defined relative to the limb on which they attach to. Yeah.
So any muscle force basically is the component of the force alone is enough. We don't need a component to the length because it's already defined relative to the joint
Exactly.
itself. Okay.
Exactly. Yeah. Mm-hmm.
But with the other two, their coordinate system isn't defined relative to the arm, so we need to put a theta component on their length, right?
Exactly. Yep.
Okay.
Mm-hmm. Yep. All right, question. So I'm having trouble seeing why it's sine theta 2, not cosine theta 2. No, great question. So let's go ahead and draw it out again. It's a little bit harder to see here because it is slanted. Okay. And so let's go ahead and draw the arm like this. Okay. And so let's say that this long orange line is the arm. And then we'll use green again for the muscle force. Okay. And so this is FM. And this right here is theta 2. Right. And this blue dot right here is going to be the joint, right? And so remember, we're summing up the moments around this joint, right? And so just like we did last time, we can break up this FM into two different components, right? And so we have the horizontal component, and so we call this, or I shouldn't say horizontal. I should say that we have the component along the length of the arm, okay? Okay, so I'll call that FMA. And then perpendicular to the arm, we have FM perpendicular, okay? Perpendicular. The cross goes on the bottom, yep. And so in this configuration here, the only component of this force that's gonna have a rotational component, or the only one that's gonna contribute to the moment, is gonna be FM perpendicular, right? Because this FMA, you can see it's pointed straight at the joint, okay? And any force that passes right through the joint is not going to contribute to rotation at all, right? And so it's the same reason why we don't consider the joint reaction forces in our moment equation, is because they don't make any contribution to the rotation. Yeah, and this component right here, FM perpendicular, is the sine component, right? And so that's going to be basically this guy right here. Okay. And so if you draw the triangle here, and so here we have theta 2, this is a right angle, we have FM, okay? If we want to get this vertical component here, we have FM sine theta 2. Yep. Mm-hmm. All right. Right, and so let's go ahead and compare this result here with our previous result, with our previous example, okay? Because we have two things that are kind of going on here, because we have this guy, which is new, sine theta a, right? And so because we've moved the arm downwards, we have a contribution to that with respect to the angle of the arm, okay? And we also have sine theta 2 here, okay? And so let's take the ratio between the answer from the previous example and this one, and see, you know, how this ratio depends on these angles. Okay. Okay. Any other questions on this? Okay. All right. So let's go ahead and take the ratio. And so I'm going to call the result from our first example today. I'll call it FM1. Okay. And then the result from the second example we did, we'll call it FM2. Okay. All right, and so we're just going to take the ratios. And so let's go ahead and write in FM1. And so FM1 was WA LA plus WLW divided by LM sine theta. I'll go ahead and call that one theta 1. Okay. And so theta 1 was the attachment angle from the previous problem. Okay. And now we're going to divide this by FM2, which is what we just found, right? And so FM2, if we just invert it from what it was before, we have sine theta A on the bottom, we have sine theta 2 up top, okay? Right? And then what we have here is LM divided by WA LA plus WLW. Okay. All right, question. For LM, why did we not also have a sine? Was it because it was already encompassed by the sine theta 2? Yes. Yeah. So we do have a sine for that LM on the second one. I just pulled it out of the denominator. Yeah. And the reason I did that is because you know, when you take the ratio of these two forces, we see here that we have this kind of big term right here, or actually I should say we have this guy right here, okay? And then we have this guy right here, okay? And these two are exactly opposite. And so we're just going to go ahead and cancel these two out, okay? And so all we're left with for the ratio is we have FM1 divided by FM2 is equal to sine theta 2 divided by sine theta 1 and sine theta A, okay? And so the ratio of the forces in those two configurations depends on this ratios of sines, okay? All right. And so at this point, you know, let's plug in some typical angles for this, and let's see, you know, which configuration is the deltoid going to, you know, work harder, okay? All right, so let's plug in some typical values. And so let's say that, you know, just like I mentioned before, so let's say that the attachment angle in the first configuration was 30 degrees, okay? Okay. And so remember, theta 1 is the attachment angle for the deltoid onto the humerus, okay? And theta A, let's say that we lowered our arm by an amount of 25 degrees. And so, you know, we just lowered a modest amount, okay? And so the angle that our arm makes with our, you know, with our sides here is going to be 65 degrees, okay? Right. Theta 2, let's say that, you know, as a result of moving our arm downwards, then the attachment angle between the, you know, between the deltoid muscle and the arm, that has lowered to 25 degrees, okay? All right, so these are fairly typical numbers for these configurations, okay? And so let's go ahead and plug this in, and let's see what we get for our ratio. Okay. All right, so go ahead and plug it in. We have sine theta 2, and so theta 2 here is 25 degrees. Okay. And the denominator we have sine theta 1, so we have sine 30. Okay. And then we have a sine 65. Okay. All right. And so we have kind of two competing effects here. And so on the one hand, you know, by lowering the attachment angle, you know, that's going to make this numerator smaller, okay? But by lowering the arm, it's going to make the theta A term smaller as well, okay? So we have kind of two things getting smaller at the same time. One is on the numerator, one's on the denominator, okay? And so let's see kind of what we get from our result, okay? And so if we plug all this into our calculator, what we get is 0.933. Right. And so since this ratio is less than 1, this means that the deltoid is exerting more force in the second example, okay? Okay. Right. And the main reason the deltoid is exerting more force in this scenario is that the attachment angle went down, okay? And so what this tells us is that the attachment angle has a very strong effect on how much muscular force or how much force the muscle has to exert, okay?
Professor, I have a question about this.
Yep.
Just when it comes to like general real life application.
Sure.
So let's say, for example, we have like two people that weigh the same, have like almost the same percent muscle mass relative to their body weight, have been training a similar amount of time, etc. Right?
Mhm.
Like their proportions are almost the same. They have the same length arms and stuff. Like I'll just use bench press as an example. So let's say that one person has muscle fibers that attach onto their pecs and their shoulders and their triceps, you know, which are all the main muscles that you use for benching. Let's just say all of those are closer to 90. Are they automatically going to be stronger than the other person who has muscle fibers that are less, that are, you know, closer to 0 as opposed to closer to 90, because their muscles can automatically exert more force on the weight?
Yeah, it's definitely going to be easier for the first person for sure, because much more of their muscle force is actually going towards, performing the action, right? And so, in this example here, if we kind of break down a muscle force into its two components, right? You have one component that's, it seems like it's not doing anything because it's just going right into the joint. But this is the component of the muscle force that actually works to stabilize the joint too. And so for the first person that you mentioned, they're not going to have as much of this, okay? And so it's going to be a lot easier for them to perform the actions because their perpendicular component is much higher. But they also might be at a higher risk of injury because their muscles are, they're not doing as much to stabilize the joints. But whether, one is stronger than the other one, that also depends on, how much raw tension the muscles can exert too. But, if we assume, like you said, that, both people have the same muscle mass and let's say that, all their muscle fibers can exert the same tension, then the first person will have a much easier time, lifting the weights compared to the other person. Yeah. All right. Any final questions? Yep. Any final questions on this before we talk about some common injuries for the upper extremity? Okay. All right. So let me go ahead and share my laptop screen really quick. All right. Okay. And so before we close out this unit on the upper extremity, I did want to talk about some common injuries that you can have for the upper extremity. Okay. All right, and so the upper extremity, mostly is comprised of, I would say, 3 different sections here. And so, the first one being the shoulder, the second one being the elbow, and the last being kind of the wrist and the hand and the fingers. Those are all kind of clumped together. Right? So let's talk about the shoulder. Right? And so for the shoulder, what tends to happen a lot for the shoulder is that they tend to become dislocated. Right? And so remember what we talked about is that, your shoulder joint is one of the most flexible joints that you have in your entire body. Okay. And a lot of that is due to the fact that your shoulder is fairly unstable. Right. And so, this is a fairly good picture of it where you have kind of this pretty large head of the humerus right here. Okay. and it's kind of fitting into this kind of really narrow socket right here, right? And so you can see that this socket is like, not really big enough to kind of really encapsulate this entire, sphere right here, okay? And so because of that, the shoulder can move around a lot, but it's also susceptible to a lot of dislocations, okay? All right, and so generally, if you want to talk about which directions that dislocations occur, they most often occur in the anterior direction. And so remember, anterior means towards the front, okay? Posterior to the back, and also inferior, which is downwards, okay? And so those are the most common directions for your dislocations, just based on the shoulder, okay? And so you can have dislocations happen in the superior direction or upwards, but this is pretty uncommon because, I know what I have listed here is that, you have fairly strong ligaments here that protect it from that direction, right? And so that's absolutely true. But you also have this little bit of a lip from the from your scapula that also kind of prevents it from going upwards as well. And so it's less common. That's not to say that it's impossible, but it's a lot less common for you to see shoulders, dislocate upwards. And usually it's some kind of traumatic injury that kind of causes it to dislocate that way. Okay. All right, and so just like, all dislocations, this usually results from sustaining some kind of large external force, right, at the joint. And in particular, your shoulder joint is most susceptible to dislocations when it's abducted and externally rotated, right? So remember, abduction means your arm is upwards, okay? And externally rotated means that your hand is supinated, okay? So your palm is facing up. And so that's generally, that's kind of the most vulnerable position for you to get a dislocation. Right. And if you've had dislocations before, then this predisposes you for future dislocations, because if you've already popped the bone out of the socket, then the ligaments here are just going to be just naturally weaker because they've been stretched before. Okay. All right. Another common shoulder injury is what's known as rotator cuff injuries. Okay. And so, unfortunately, I don't have a good image of this, but the rotator cuff basically consists of all the soft tissue that surrounds this the shoulder joint. Okay. And so because the shoulder joint is so loose, there's kind of a collection of soft tissue, of ligaments, of tendons around here that kind of protect it from dislocations. And that's sometimes called the glenoid capsule. Okay. But I think more informally, it's also called the rotator cuff. Okay. And so people can injure the rotator cuffs, and that's another common injury. Okay. And this generally tends to occur for people that engage in large overhead or rotational motions of their arm, okay? Because what these do is that they kind of aggravate, they kind of pinch and stretch the rotator cuffs around the shoulder joint, okay? And it can cause them to become fatigued and damaged, okay? And so, the people that are most vulnerable to rotator cuff injuries are for athletes who engage in a lot of throwing, okay? And so if you play sports like football, like if you're a quarterback, right? Baseball involves a lot of throwing. Tennis, you're swinging the racket all the time. And swimming too, because you're doing a lot of overhead strokes. That's going to put you at risk for rotator cuff injury. And also just any other job that requires a lot of overhead motions as well. Okay. And so if you're, if you're doing any kind of job and you're doing a lot of overhead motions, just kind of be careful about it and kind of monitor the state of your shoulder, because if it's starting to feel fatigued and it's starting to feel tired, and you still try to work after that, then you might be doing some long-term damage to your shoulder. Okay. Okay. Any questions on this? Okay. And so that's shoulder injuries. All right, so now let's talk about elbow injuries. Okay, and so elbow injuries are relatively not as common as shoulder ones, because the elbow is a pretty stable joint because it has pretty strong ligaments on both sides. Okay, but it is still possible to injure. Okay, and remember, one of the research questions on the homework, I'm having you look into a fairly common injury for baseball players, which is repaired with a surgery called Tommy John surgery. Okay. All right, but for a lot of other people, the elbow joint is typically subjected to what's called overuse injuries. Okay, because among the joints in your body, your elbow is the one that kind of flexes, the most, flexes and extends the most. Okay. And so, overuse injury means things like stress fractures. Okay. Okay. And these usually cause some kind of micro damage to the soft tissue. Okay. To like the ligaments and the tendons at the elbow. Okay. And these can tend to progress as time goes on. Okay. And so one common example of this is tennis elbow, okay? And so the scientific term for this is epicondylitis. And so this involves micro damage to the ligaments and the tendons on the lateral side of the humerus, okay? And so that's on the outer side. And so that's opposite of Tommy John surgery, because Tommy John is it involves an injury to the inner elbow, but this is for the outer one, okay? And so it is possible to dislocate your elbow when large impacts are placed at the elbow. Okay, and so one of the most common situations where people dislocate their elbows is when you fall and you kind of brace yourself with outstretched arms. Okay. All right. Any questions on this? All right. And so finally, we have wrist injuries. Okay. And so your wrists, even more so than your elbow, are used continuously in many daily activities. And, and this has only gotten worse in the technology age, because, a lot of us are on our phones all the time. A lot of us are typing on the computer. We're using mouses. Okay. And so even though all these activities may not seem like they're that stressful, the fact that we do them so much and all the time, it places a lot of strain on the wrist. Okay. All right, but just like any joint, it's possible to get strains of dislocation. Okay, and again, this can happen when you're bracing yourself for a fall. Okay, but probably the most common wrist injuries that you'll see in most people are overuse type injuries. Okay. All right, and so one very common syndrome that's becoming more and more common is carpal tunnel syndrome. Okay. All right, and so the direct cause of carpal tunnel syndrome is still relatively under research, but generally, we all agree. Generally, scientists agree that carpal tunnel syndrome, the reason it causes you pain is that you get some swelling in the tissue in your wrist area. Okay, and then what that does is that if this tissue right here starts to swell, actually this is a better example. Okay, and so let's say this tissue right here starts to swell. This is going to start pinching the nerves that you have inside your wrist. Okay, and so the one that actually comes under the most pain is this little nerve right here that's highlighted in yellow. Okay, and this is what's known as the median nerve. Okay, and so as the muscles or the tendons or the ligaments in the wrist start to become inflamed because of their overuse, then by nature of becoming inflamed, then the tissue is going to grow in size. Okay, and when the tissue grows in size, it's going to start pinching on these nerves, which is what gives you the sensation of pain, or for some people it becomes tingling, or for some people it turns into numbness. Okay, and so depending on the degree of how much this nerve is pinched, then it's going to cause different effects. Okay, all right, and so the best, or one way that you can kind of decrease your risk of carpal tunnel syndrome is making sure that your wrists are they're at an ergonomic position when you're typing at the keyboard or you're doing other stuff. Okay, and one thing that helps with that is one of those little soft, really soft pads that you can put in front of your keyboard, right? And so you literally rest your wrist on it, and it's kind of a soft, almost like a pillow, like a cushion. And so that's to make sure that your muscles and your tendons and your ligaments in your wrist don't sustain any unnecessary stresses, and it reduces the risk for them to become inflamed. All right, any questions on this before we move on to lower extremity stuff? Okay. All right, so that's the upper extremity, right? And so that's one full unit. And so basically the way that we proceeded through this unit right here is how we're going to proceed through the lower extremity, and then finally for the spine as well. Okay, and so we're going to start with an introduction to the anatomy and the general kind of characteristics of that part of the body. Okay, then we're going to do a lot of problems involving static analysis. Okay. and then we'll close by talking about some of the injuries. Okay. All right, so let's go ahead and move on to the lower extremity. Okay, here are the learning objectives. Okay. All right, and so let's start by talking about some of the general characteristics of the lower extremity. Okay, and so when I talk about the lower extremity, what I mean by this is the hip, the knee, the ankle, and the foot. Okay, and the two main responsibilities for the lower extremity are weight bearing and also locomotion. Okay. And so these actually, the lower extremity is really interesting because, these two responsibilities here actually require a very different set of skills, right? Because on the one hand, with the weight bearing, you want your lower extremity to be, fairly strong because, it's bearing a lot of the weight of your body, right? And so the characteristics that, that you would want in weight bearing are, your muscles and your bones are really, thick, they're really strong, okay? But for locomotion, just like the upper extremity, you also want the lower extremity to be fairly mobile. You want it to be, not so, you want to have a good range of flexibility. You want to have a good range of motion, okay? And so generally, these two are kind of opposites, right? Because just like we talked about for the upper extremity, your muscles of like your shoulder and your arms and your and your wrist are not usually that big because they're built for fine dexterous motions and movement, right? And so the lower extremity kind of has to toe the line in between these two responsibilities by first of all, they have to be strong enough in order to bear your weight, but they also have to be flexible and fast enough so that you can have a good locomotion, right? Because having strong legs is great, but if you're being chased by a bear, you also you need more than just weight bearing. You also need to be able to move your legs really, really quickly too, right? Okay. And so the reason I'm kind of jumping from the upper extremity down to the legs is I'm kind of progressing through the different parts of your body in terms of range of motion. Okay, and so the range of motion that you see in the lower extremity is of course lower than your upper extremity, just because you're not going to be sewing a sweater or performing surgery with your toes. Okay, and so you don't need that much dexterity. Okay, but it is a lot higher than your spine. Okay, and so we're kind of in this in between the upper extremity and the spine. Okay, but with that said, you do have some very stable joints of your lower extremity. The most stable of which is the hip. Okay, and so the hip is by far the most stable joint in the body just because of just how it's designed. Okay, and the lower extremity also has a lot of very large and powerful muscles to allow for effective locomotion. Okay, and so the muscles in your thighs, so your hamstring and your quadriceps, are probably among the biggest muscles you have in your body. Okay, because they have to not only support your weight, but they also have to move you as well. Okay. And another key responsibility for the lower extremity is balance as well. Okay, and so making sure that you're always standing upright, you're not tripping over yourself, you're not falling. A lot of that responsibility falls on the lower extremity. Okay. All right, any questions on this? Okay. All right, so let's talk about the bones of the lower extremity. Okay, and so the lower extremity is going to start at the hip bone up here, and then it's going to progress down to your feet. Okay. All right, so let's start with the pelvic bone. Okay, and so the pelvic bone is this guy right here. Okay. And so I call it the pelvic bone, but it actually consists of several bones. Okay, and so the first of which being the hip bone. Okay, the hip bone being kind of the Dumbo-looking bones on the side right here. Okay. Next, we have the sacrum, and so the sacrum is actually also technically part of the spine, and so the sacrum is, and so we'll talk about it, once we get to spinal biomechanics. Okay, so the sacrum is basically this guy right here. Okay, and then the last bone in your pelvis is the coccyx, which is the tailbone. Right? And so that's going to be this guy down here. Okay. All right, but I would say the most defining characteristic of your pelvic bone is actually this part right here. Okay, and so basically where the pelvic bone attaches to the thigh bone, okay, It's called the acetabellum. Right? And so what this is known for is it's known for its very deep and spherical cavity. And so, you know, the head of the thigh bone of the femur fits into this cavity so well, and that's what makes the hip such a stable joint. Okay, it's these two almost kind of fit together like, you know, like a glove. Okay. All right, and so let's go ahead and move on downwards. And so next we have the femur, and so the femur is this large bone right here. Okay, right. So this is better known as the thigh bone. Okay, and so in terms of the long bones in your body, and so, you know, remember, you know, the reason these are called long is because they're, you know, they're shaped like shafts. And so among the long bones in your body, your femur is the biggest one. Okay. And the main goals for the femur is to provide the body with structural stability. Okay. And a lot of attachment ankles for all the a lot of attachment locations for all the various muscles, you know, in the thigh as well. Okay. And the you know, and we've talked about it, you know, just before, but, you know, the most defining characteristic of the femur is this very large head. Okay. And this inserts right into this acetabellum. Okay. And this femoral head right here is actually really big, and it fits into a very big socket right there. Okay. And so it's actually really hard to get this you know, this thigh bone out from the socket. And so, you know, you'll see that hip dislocations are extremely rare because of how stable this joint is. All right, and so the next bone that we're going to talk about is the patella. Okay, and so this is your kneecap. Okay, and so this is a small flat bone that's located on the anterior side of the knee. Okay, and so the main responsibilities for the patella is that it covers and protects the anterior surface of the knee joint. Okay, because right underneath the patella you have kind of a complex network of different ligaments. Okay, and different tendons and different soft tissue. And so this patella here kind of acts like almost like a helmet or shield to protect those parts from impacts. Okay. All right, and so next we have both of our calf bones here. Right? And so let's start with the tibia. Okay, and so you can see here that, you know, we have two calf bones. We have one that's a lot bigger than the other one. Okay, and so this bone right here is your tibia. Right, and so between your calf bones, this is the bigger one. Okay, and so this is the bone that's actually in front, and so this is more anterior. Okay, and the main responsibilities for the tibia is that it has a very large and flat head right here. Okay, and so this region of the tibia right here is often called the tibial plateau. Okay, and so this is what forms the kind of the bottom half of the knee joint. Okay, and the tibia plateau and the reason it's kind of big and flat like that, remember, is that, you know, the knee has so many ligaments that attaches inside it, right? And so they all attach to the tibial plateau to some degree or the other. Okay? Another reason why it's kind of large and flat is because you know, your knee joint is subject to a lot of impacts, right? And so the large surface area at the tibial plateau means that those impacts are going to be spread across a larger surface area. And you actually have a piece of soft tissue that covers the tibial plateau too, called the meniscus, and so that also helps with you know, with impacts. All right, and so the other bone that you have in your calf is your fibula. Okay, and so this is the smaller bone. Okay, and so the fibula here is it's smaller and more slender. Okay, and it attaches at 2 points, right? And so on the top part. And so the fibula is not part of the knee joint at all. And so on the superior side of the fibula, it actually attaches to the tibia right here. Okay. And then on the inferior side, the fibula is going to attach to the lateral part of the ankle. Okay. And so it's going to attach onto the outer ankle. Right there. All right. And then so besides those, we also have our tarsals and metatarsals. Okay. And so these are just your foot bones and your toe bones. Okay. And so this right here would be your tarsals, and this right here would be your metatarsals. Okay. All right. Any questions on this? Okay. All right, so let's talk about the joints. And so there's there's a fill with text in there. I forgot to fill that in. But basically, there are three main joints here in the lower extremity. Okay, and so first we have the hip joint, right? And so we've already talked about the hip joint as the most stable joint in the body. Okay, and so it consists of the spherical head, and that inserts into the spherical cavity of the pelvis bone. Okay, and your hip joint right here is almost as close as you can get to kind of what I call a true ball and socket joint. Okay, and so even though your shoulder is characterized as a ball and socket, also remember the cavity in your shoulder is actually really shallow, and so it's kind of a ball and groove. It's not, your shoulder's not really a ball and socket. I would call it more of a ball and groove joint, and so your hip bone is actually a true ball and socket. Okay, but with that said, it's even though it can allow your hip to do all these kind of complex motions, the flexibility of this joint is actually lower than that of your shoulder. Okay, and so even though anatomically speaking, it is a ball and socket, but you also have a really dense and complex networks of ligaments that kind of prevent your hip from doing all kinds of really crazy motion. And so unless you're an Olympic gymnast, you're not going to be able to do a lot of things with your hip. And so even though it can kind of rotate in all these different planes, because it's so stable, it doesn't actually let you do a huge range of motions unless you are yourself a very flexible person. All right, so next we have the knee joint. Okay, and so the knee joint is actually interesting because it actually consists of three bones. Okay, and so on the one hand you have the two bones that are kind of the limbs of the knee, right? And so you have your femur, which is in your thigh, and then your tibia, which is in your calf, right? And so those are kind of the two kind of, I would say, traditional bones that you have at your knee joint. Okay, but you also have the patella, right? And so the patella is also a bone that comes at the knee, but it doesn't really have a huge effect on the limbs or the motion. Okay, and so your knee joint here it's mostly a hinge joint, and so it's very similar to the elbow in that sense. Okay, and so the primary motions that the knee allows are flexion and extension. Okay, but it also allows for some sliding motions as well. Okay, and so you kind of have some lateral movement of your knee as well. Okay, and actually your patella too, you can kind of if you kind of extend your leg all the way, you can kind of jiggle your patella around a little bit. Yeah. All right, and so the last joint that we have in the lower extremity is the ankle. Okay, and so the ankle, when we talk about the ankle joint, it consists of the inferior side of the tibia, and the fibula and the tarsus. Okay, and so similar to the knee joint, it involves more than two bones. Okay, mostly because the tibia and the fibula kind of come down and attach onto the ankle at the same location. Okay, and so all three of these joints kind of consist of the ankle joint. Okay, and so the primary motions that the ankle joint allows are plantar flexion and dorsiflexion. Okay, but it also allows for some degree of rotation as well. Okay, and so you can kind of move your feet kind of side to side, but the primary motions are going to be plantar flexion and dorsiflexion. Okay, and so a little bit less flexible than the wrist, but not by that much actually. It's just that we don't think of our ankle being that dexterous because we can't really do much with our toes most of the time compared to our fingers. Okay. And in terms of stability, remember the ankle is one of the more unstable joints in your body. Just because the ligaments just aren't really strong down there, and also the bones don't really connect all super well either. All right, any questions on this? Okay. All right, and so let's talk a little bit about the tendons and ligaments. And so I think I'll start this a little bit, but then we'll we'll of course pick this up on Wednesday. Okay. All right, and so let's talk about the cruciate ligaments, right? And so your cruciate ligaments are your ACL and your PCL, okay? And those stand for the anterior and posterior cruciate ligaments, okay? And so these are the ligaments that actually occur on the inside of your knee, okay? And the reason they get their name, cruciate, is because they kind of form this cross on the inside, okay? And so, their primary job is to limit forward and backward sliding of the femur on the tibial plateau, right? And so the fact that your knee can't slide, your thigh can't slide forward relative to your lower leg is because of your ACL and the PCL, okay? Right, and then, compared to a lot of other joints in your body, your knee really relies on these ligaments because, as you can see, that your femur comes in and kind of like a two-pronged motion here, and then your tibia here is basically all flat. And so these two bones, if you try to stick them together without any ligaments, it's really easy for them to slide apart. And so, these ligaments actually do quite a lot of work in stabilizing your knee. Okay. All right, any final questions on this before we wrap up for the week, or wrap up for today? Sorry. Okay, all right, and so that's all we got time for today. And so it's 5:15, and so on Wednesday we'll pick this up from here, and so we'll finish talking about the ligaments and tendons of the lower extremity and the muscles, and then we'll start doing some problems again. Okay, all right. So thank you everyone for tuning in. I know it was kind of a last-minute change to go virtual, so I appreciate your guys' flexibility. And hope you guys have a good rest of your day, and I'll see you on Wednesday.
Thanks, Professor.
Thank you, Professor.
Thanks, guys.
Thank you, Professor.
Thanks.
Actually, Professor, quick question,
Sure.
if you don't mind.